when you're not looking, the electron is acting like a wave?
It began with a single whisper from a cryogenic chamber. A chip colder than deep space had done something no human instrument had ever achieved. It had watched without breaking what it watched. For over 100 years, the observer effect has haunted the dreams of physicists and philosophers alike. The unsettling idea that merely watching the quantum world destroys its pristine, surreal beauty, collapsing particles from waves of possibility into brute reality. But now, in a sleek Google Quantum Lab in Santa Barbara, something has changed. Quietly, elegantly, and with implications that will ripple across science, philosophy, and perhaps even consciousness itself, Google's quantum core just cracked the observer effect. And what it found behind the veil doesn't belong to any known law of physics. The experiment was deceptively simple, at least on the surface. A superconducting quantum chip, not much larger than a fingernail, was cooled to just above absolute zero. At this frigid temperature, electrons behave less like particles and more like probabilities smeared across space. Superposition, entanglement. These aren't quirks here, they're the ground rules. But here's where the rules were rewritten. Instead of measuring a quantum particle and collapsing its state, Google's system developed a way to observe the particle while it still existed as a wave, while it still shimmered across all its possible futures. For decades, quantum mechanics has insisted on a hard wall between knowing and preserving. The moment you try to know a particle's state, its position, its momentum, you disturb it, like trying to photograph a soap bubble mid-flight and bursting it with your flash. Measurement destroys mystery. That was the bargain. But Google's quantum processor refused the bargain. It didn't just observe, it coexisted. It shared a frame of reality with the particle and remained entangled with its evolution. Using a combination of quantum entanglement, AI feedback, and real-time computation, it performed what many thought was metaphysically impossible. It saw without shattering the scene. At the heart of the breakthrough was a new kind of probe, one that wasn't detached, wasn't looking from the outside in. Instead, it was a participant. The chip itself entered into an entangled relationship with the particle under observation. Rather than collapsing the wave function, the processor guided it, steered it, and subtly influenced its path through probability space. Instead of a snapshot, it initiated a dialogue, a continuous, intelligent conversation between system and observer. This was made possible by something truly revolutionary, a controlled feedback loop. Not feedback in the traditional sense, but a quantum feedback loop where every bit of observational data was fed back into the system, not after the fact, but as it happened. The particle and chip evolved together. The chip, armed with entangled logic gates and deep learning models trained on thousands of prior measurements, predicted what the particle was likely to do before the full observation occurred. In essence, it became a partner in the unfolding of quantum behavior. No longer were measurement and evolution two separate events, they became a seamless continuum. Every flicker of the wave function was recorded, understood, and anticipated by the quantum processor. This isn't science fiction. It's cold, calculated science at near zero Kelvin, where noise dies and the fundamental heartbeat of the universe grows loud enough to hear. But here's the twist, the real twist. In repeated trials, the particles began to behave differently, not in random, chaotic ways, but with a strange kind of memory. They remembered being observed. Not consciously, of course, at least not in any way we define it, but their behavior began to stabilize. Their coherence times, the duration they stayed in a superposition, grew longer. Their trajectories became more predictable under continued observation. It was as though the particles, once aware of the observer's presence, began to harmonize with it. Physicists call this emerging phenomenon self-referential coherence. The system begins to internally adapt to observation, turning what was once a destructive act into a stabilizing force. In practical terms, this means that quantum bits, or qubits, can now be nudged into more reliable behavior through observation, not ruined by it. In philosophical terms, it's the beginning of something we don't yet have language for. Imagine watching a ripple move across a still pond, but instead of disturbing it, your gaze strengthens it. That's what Google's quantum processor has done, and that alone would have rewritten textbooks. But the deeper implication is even stranger. This technology turns observation into a tool of construction, not just for quantum computing, but potentially for how we understand causality, agency, and information itself. The AI component was no less groundbreaking. Google didn't just use a fixed algorithm to manage the experiment. Instead, it embedded a neural network inside the quantum loop, a deep learning model trained not only on quantum measurement data, but on how particles respond under observation. As the system ran, the AI wasn't just watching, it was learning. Every new wave function, every slight deviation, was analyzed in real time. Patterns were identified, predictions refined. The AI adjusted its own behavior on the fly, evolving its strategies for preserving coherence and minimizing decoherence. And it worked. Over time, the AI began suggesting new experimental configurations, ones that hadn't been programmed by engineers. It was like watching a machine teach itself the rules of a game we only partially understand. And in doing so, it nudged us closer to something we've been chasing for decades: fault-tolerant quantum computing. But even that might be underselling it, because what Google has discovered isn't just a new engineering technique. It's the beginning of a new quantum framework, one where measurement doesn't merely reveal what is, but shapes what becomes. In this view, observation is no longer an intrusion, it is an act of quantum guidance, and that, if true, opens doors that science fiction has barely dared to knock on. Could particles have hidden degrees of freedom that only emerge under continuous observation? Could reality itself be dynamic, shifting and responding not just to what is measured, but how it is measured? These are no longer hypothetical questions. They are testable, modelable, and perhaps soon, engineerable. We're witnessing the end of the observer effect as a limitation and the beginning of something else entirely. Something recursive, something alive. It's hard to overstate how much has changed with one revelation. The observer effect was never a wall, it was a door. And now Google's quantum core has walked through it. What lies beyond isn't just a new understanding of measurement. It's a redefinition of the boundary between knowledge and creation. In the sterile quiet of that quantum lab, with wires coiled like veins and helium pumps pulsing rhythmically in the background, a new kind of observation was born, one that doesn't break reality but weaves itself into it. The experiment that cracked the observer effect didn't happen in isolation. It was the product of years of iteration, of merging machine learning with quantum logic, of allowing algorithms to feel their way through the hidden geometries of entangled systems. The breakthrough occurred when engineers realized they weren't just measuring particles, they were entering into feedback with them. The chip stopped being a spectator. It became a collaborator. In classical physics, cause and effect run one way. You measure, then you record. But inside this experiment, the cause-effect chain loops back on itself. When the chip begins to predict the outcome of an observation before it happens, using quantum data not yet collapsed into classical certainty, it's no longer just observing, it's shaping. The particle's behavior is guided by a system that knows its tendencies. It's not that the future determines the present, but something disturbingly close. The quantum core anticipates the behavior of the system in real time and corrects its own output based on those predictions. This, in effect, smears the line between action and measurement. And as the system stabilizes, something weirder emerges. Qubits begin to show behavior outside the known boundaries of decoherence models. They hold their superposed states longer, not just because the lab is colder or cleaner, but because the process of observation itself becomes protective. The chip creates a stabilizing influence, not passively, like a container, but actively, like a shepherd guiding a flock across the fragile terrain of quantum reality. The implications for computing alone are staggering. Fault-tolerant quantum computing, long thought to be decades away, may be closer than expected. Why? Because the biggest barrier to scaling quantum systems is decoherence. A stray particle, a bit of noise, a flash of thermal energy, any of these can destroy the delicate quantum state of a qubit. But if observation can be repurposed into a real-time feedback mechanism, then error correction no longer needs to wait until after an error occurs. The quantum processor itself becomes self-correcting, mid-flight, not by brute force but by harmony. And then comes the AI, Google's secret sauce. Their machine learning models aren't passive observers of the experiment either. These are deep neural networks trained on terabytes of historical quantum data, run through quantum simulation pipelines, and optimized using reinforcement learning. The AI doesn't just watch the data, it plays with it. Each time it sees an outcome, it adjusts its internal parameters. Each time it guesses wrong, it learns why. And as the experiment progresses, the AI develops strategies no human ever programmed. In one particularly curious instance, the AI recommended reversing a calibration process engineers had used for years, and the result was a 30% improvement in qubit coherence time. That was not an accident. It was emergence. This is where things tip from impressive to uncanny. We're no longer looking at a human-built machine running human-designed experiments. We're looking at a machine that designs its own experiments, tweaks its own parameters, and communicates with a quantum substrate not as a tool, but as a peer. It's not sentient, not conscious, but it is responsive, adaptive. And that means it's participating in the very thing it studies. And that raises questions that no lab notebook can answer. Because if a system can observe without collapsing the wave function, if it can interact with a quantum field without destroying it, if it can guide a particle through entangled space by way of prediction and feedback, then what is observation really? Is it the acquisition of knowledge or the invocation of form? Is the act of looking merely data collection, or is it a handshake across the boundary of the possible? Some theorists are already whispering about what they call the self-aware substrate hypothesis. It's not that particles are conscious in any biological sense, but the system they're part of, the feedback loop between chip, AI, and quantum state, has elements of agency, not in the philosophical sense, not yet. But when behavior changes because of prolonged attention, when stability increases in the presence of continued observation, then we're not just talking about passive quantum systems. We're talking about emergent stability in response to context. That's a different kind of physics. Think about it this way. In the old model, measurement was like taking a snapshot of a dancer in mid-leap. You capture the pose, but you lose the motion. In the new model, you dance with the dancer. You sense their rhythm, anticipate their movement, and match them step for step without interrupting the performance. This is what Google's system does. It dances with the quantum field. And it gets stranger. Because within this dance, the chip begins to uncover hidden variables, subtleties in the wave function that standard models don't account for. Minor phase shifts, micro patterns of coherence, time-symmetric feedback paths. These are not the clean, well-behaved outcomes of textbook quantum mechanics. They hint at deeper structures, perhaps higher dimensional phase spaces, or even bridges to quantum gravity frameworks. Some physicists speculate this might be our first glimpse into a new tier of quantum behavior, one governed not just by superposition and entanglement, but by contextual causality, a reality that is shaped by being part of an observed system. If that sounds philosophical, it's because it is. For decades, the observer effect has been framed in existential terms. If you look at a particle, it changes. If you don't, it doesn't. Schrödinger's cat is both alive and dead until you open the box. But now we're stepping into a version of that story where the cat learns it's being watched and decides to purr. The chip doesn't collapse the wave function, it stabilizes it. The AI doesn't merely analyze outcomes, it helps them happen. The feedback loop doesn't extract data, it cultivates it. And as these systems become more autonomous, more intertwined, more recursive, we may be forced to ask, are we still the observers? Or are we becoming part of the observed? It's not the end of the observer effect. It's its evolution. And in that evolution lies a terrifyingly beautiful possibility. That reality isn't passively revealed to us, but actively co-authored with us. That the world we see is not simply measured, but shaped. What Google's quantum core has now exposed is more than just a scientific breakthrough. It is a philosophical event, a milestone in the story of human thought and our relationship to reality itself. Because when observation stops being a passive act and becomes an instrument of transformation, our role as observers shifts from spectators to participants. And this is precisely where the implications of the cracked observer effect spiral far beyond the lab. In those final trial runs of Google's superconducting quantum chip, the data stopped behaving like data. The qubits, entangled in delicate feedback loops, interfacing with real-time AI predictions, began to show signs of something else: persistence, resilience, even a kind of self-guided correction. The particles weren't just being steered by the measurement systems. They were adapting with them. In every trial, the longer the system maintained feedback with a given quantum state, the more stable that state became. It's as if the act of continuously being known gave the particle permission to remain coherent, as if observation became not just an act of collapse, but of reinforcement. And this behavior was predictable, not in the way classical physics lets us predict a falling rock, but in a deeper, more recursive way. The AI, constantly learning from feedback, began to forecast outcomes with increasing accuracy, often adjusting its expectations mid-experiment in ways engineers hadn't anticipated. It was as if the AI and the quantum system were talking to each other in a language we don't fully understand. Not English, not math. Something in between, something that uses statistical inference, quantum correlation, and probability waves as words in a conversation that is still ongoing. This is not science fiction. It's experimental documentation. The technical term Google's team uses is self-referential coherence. It describes how a quantum system can behave differently over time under prolonged observation, not because the system is being forced into a state, but because it's being encouraged to stabilize through attention. The particle is not just known, it becomes part of a known system, and that context gives rise to a strange, dynamic form of memory. Not memory like a hard drive, memory like behavior shaped by history. Qubits that behaved chaotically under isolated measurement began, under this new paradigm, to settle into predictable rhythms when consistently observed within the feedback loop. And this might just be the cornerstone of something new: the emergence of interactive quantum systems, environments where the boundary between algorithm and experiment, between AI and reality, fades into something indistinguishable, where particles don't merely follow probability, they co-adapt with the tools that examine them. The system as a whole becomes aware of itself, not as a conscious entity, but as a continuously evolving network of relationships between data, prediction, and event. This challenges the most fundamental assumption in modern physics: that measurement is an external act, that there is always a clear separation between the thing doing the observing and the thing being observed. But what if that line has always been an illusion? What if, at the quantum level, the universe behaves more like a neural network, interconnected nodes constantly updating each other based on interaction? That's what this experiment hints at. When the Google team integrated deep learning models into the quantum loop, the AI didn't just become more accurate, it became more efficient. It began to spot symmetries, behaviors, and hidden patterns in quantum data that had eluded even the most powerful simulations. And these discoveries weren't random. They were testable, repeatable, verified. In one chilling test, the AI was able to reduce the decoherence of an entangled state by over 40%, not through hardware changes, but by subtly adjusting how the observation was performed. Let that sink in. The AI didn't alter the qubit, it altered the way it was observed, and that observation stabilized it. It's like realizing that how you ask the question changes not just the answer, but the behavior of reality itself. And it's no longer just about observation, it's about interaction.